Welcome, everybody. It's my pleasure today to introduce Yulia Gell, from the University of Texas at Dallas, and she'll be telling us about topological clustering of multi-layer networks and beyond.
Thank you. So first of all, I'd like to say that I'm not a topologist. I have a math background, but I've been doing statistics for the last 20 years. But I find the bridge between TD and statistics fascinating, and I hope that statisticians would use more topological methods. So what I'll talk today, I start from multi-layer networks as a motivation, but you'll see that the tools that we are trying to develop are applicable way beyond multi-layer networks. And since it's applied seminar, so I'll start from a really applied problem. So I'll tell how we came up with this multi-layer network clustering with TDA. And then I will proceed to some statistical properties, some clustering stability of the associated tools. So it's very, as I said, it's very applied problem. So your house insurance, okay? So how's your house insurance is affected by climate dynamics, okay? So when I talk about climate dynamics, it depends where you are. You may be more worried about hurricanes and so on, but beyond hurricanes, there are many other problems, like for example, heavier than normal rain or stronger than normal wind speed that may affect your roof or your basement, walls, and so on. So it creates damages to houses, and eventually insurance companies pay for this, and they don't want to pay forever because those damages are not covered by reinsurance. Those are not catastrophes. And so they may reduce coverage in certain areas, but they're already doing it, or increase the premium. So we started this project a number of years ago when actually insurance company approached us and asked, like, what can we do to quantify like more vulnerable areas, less vulnerable areas for short-term forecasting, medium-term, long-term, and so on. So it's a big problem, and there are many papers on this. And one interesting, I'll skip all like most of the details here, just trying to bring the point. The problem is largely overlooked comparing to catastrophes in insurance, because catastrophes involve $1 million immediately, yes, like Hurricane Harvey, for example, or the recent Texas snowstorm. But the ones that I'm talking about are called low individual, high cumulative impact events. And they're much less investigated. What's interesting is that it turns out that precipitation indices are much more spatially incoherent comparing to other indices of other atmospheric variables as wind speed and so on. And so here you can see the example where we look at Ontario, Canada. Those are not postal codes, but kind of similar to forward citation areas, similar to postal codes. And you see total claim amounts, total claim filed, total precipitation, average credit score, average house, and they're all very spatially dispersed, okay? So using, say, standard clustering techniques based on Euclidean distance may be not the appropriate thing, because the goal eventually try to understand which areas may be more risky, more vulnerable, yes? And you need to account not only for, say, precipitation, but you need to account for age of a house, for social demographics, for many things. So Euclidean clustering may be not really the proper choice here. So, so as I said, that given this contract with insurance company, our goal was try to understand the spatial distribution of these risky areas while accounting for all these social demographic and socioeconomic variables in a better way. Okay. And so we looked at the slow individual high cumulative impact events. Unfortunately, I cannot tell the name of a company because it was all under the, agreements that we not even mention the name anywhere, not even the data. And so the data, generally speaking, all the atmospheric data, but precipitation in particular, tend to be highly non-stationary. So those, not like processes of covariance stationary. So it's, covariance and all the statistical formulations do change over time, and non-separable. In the sense, non-separable, I mean that if you look at space-time covariance, you cannot separate that into two different parts. Okay, so your dependence over time also depends over space and reverse. Okay, so can we do something better than that? So the idea that we came up was the following. So we'll model this, complex space-time relationship between atmospheric variable. Here we particularly focus on precipitation related house insurance claims. So we'll look at precipitation, we'll look at social demographic variables, house prices, credit score, and so on, as a multi-layer network. Okay, and so we'll try to model the connection, dependency between different nodes. In our case, those are postal code areas or forward citation areas in Canada, through dependency between various variables in one layer and in between layers. Okay, so but it still becomes quite a complicated object. So yes, we'll do address dependency better, but how to draw any inference about this object, how to clustering. After that, after we created this multi-layer network, the idea is to embed this multi-layer network in some lower dimensional Euclidean space. Okay, and so in ML, it's called embedding. Yes, so we are doing embedding of this multi-layer graph in Euclidean space. And then after that, we'll look at each node in this embedded space, and we'll look at its neighborhood. Okay, and that's where TDA comes in. So we'll try to pick up shape of a neighborhood. Okay, and then we'll cluster nodes, in our case, postal code areas, based on how similar local shapes are. Okay, so we're not looking at the whole persistent homology of the whole multi-layer network or embedded object. We're looking at the local neighborhood of each node only. Okay, and then we try to do clustering based on this. Okay, so a little bit about the data. So we have the data real. That's why we can't really share this insurance data, because it's a great example of something where you can dig up privacy and security, because we know every single claim. So we can pretty much check, or with high probability, who's this house. So we know every single claim over 10 years. Okay, and we know credit score and many other parameters. Okay, so it's, and we'll use 5 variables here. So number of insurance claims, total amount of home insurance losses, okay, for each loss, average age of a house, average credit score in this area, and total precipitation. Okay, so all the atmospheric data come from NCAR, National Center for Atmospheric Research. And so I'm sure that audience is pretty familiar with a graph. So it's a single layer graph. We consider a weighted graph. Yes, so V is a set of nodes, E is a set of edges. Okay, it's undirected, and W is an age weight function. Okay, whatever it is. And now so for each, we can do a graph for each layer. And now what's about multi-layer? So multi-layer network. Okay, so it's a collection of the single layer graphs where nodes can be connected both within a layer and potentially with any other node in any other layer. okay? And as a result, we'll have adjacency matrix, which consists of both within layer matrices and in between adjacency matrix, connectivity matrices. Okay, so this is roughly how we can visualize our graph. Okay, so the truth is that we actually have a sub-case of a multi-layer network. We have a multiplex network because actually our nodes is the same across different layers because our nodes actually postal codes. Okay, so they stay the same. But connectivity can be both within a single layer and in between layers. Okay, so how to connect those nodes both within layer and in between layers? So what we do here.
And Yulia, should I think of the different layers as different times, for example?
No, it's not different. It could be different times. We haven't done it.
Okay.
Okay. Yeah, it could be different times. Here it's just each layer. For example, this layer is number of house insurance claims. So each node is a postal code. Okay, and this is just number of house insurance claims. This one is magnitude, severity of claims. This one, say credit score, average credit score. This one is average house age. And this one is precipitation.
Got it. Thanks.
Of course, they could be done over time as well, but not on this one, okay? Okay, now how to actually make all this connection between. So people in neuroscience, they usually use relation, just relation networks, okay? And sometimes also in economic and finance networks, people also just look at relation. Here, relation maybe not the best way to do because it's all, I mean, all these variables are very disparate. You see, like, you know, you have precipitation, you have house insurance claims and credit score, you know, so it's not really a feasible way to address the dependency. So what we do here, we use the something from a tool in statistics coming from generalized additive models. It's pretty old tool. It's called alternating conditional expectations. So the idea is that you have a model, you have say y versus x, and then you can transform, you can apply smooth transformations to both y and x in order to maximize r squared. So those y and x, I mean, transformations are usually splines, and you can control the degree of smoothness. And then the idea is that you do not need to have standard assumptions about correlation coefficients, about monotonicity, of course, completely bypass all Gaussianity and so on. So it's much better way to address non-monotonic behavior, but it won't be in a closed form. You'll have only the plot, and then you have a number, the highest ace. Okay, so we use here this alternative conditional expectation, and we actually pick up, we didn't do the trimming pretty much, so we looked all alternative conditional expectation across all the nodes, okay? And after that, after we created this multi-layer network, 5-layer network, and everything, pretty much everything is interconnected within this multi-layer graph. Now the goal is to embed it. Okay, I mean, potentially you can bypass embedding as well, but at that time we did the embedding in the low dimensional Euclidean space. And what the method that we used is called multi-layer network embedding. It comes from a group from Arizona State. And so the idea is of main is to have two loss functions. So this one is when you're embedding connectivity of nodes within the one layer, and this one is between among the layers. So the idea of embedding is that in embedded space, you shall preserve similarity of nodes within the same layer, and across the layers. For across the layers, here we used some kind of latent variables to preserve the similarity between the latent variables for each node across layers. Okay, so after doing that, okay, so what we got is 7. So we have a 5-layer network. We have 4 or 5 nodes in each layer. Okay, and then based on this ACE, we have alternating conditional expectation. We have 7 cross-layer dependencies. So the number of claims, of course, depends on the loss of claims. Precipitation depends on losses, precipitation, and number of claims, and age of the houses versus losses and so on. So some of them really make sense, you know. Of course, you can go deeper than that and connect every layer with every other layer as well. Okay, so now we found ourselves in the Euclidean space. So how to do this clustering? So as I said, the idea is that we try to bypass Euclidean clustering, because with Euclidean-based clustering, you will actually group points that tend to be similar geographically, okay? So how can we do something beyond that, okay? And the idea was the following. So it's actually motivated from, if you look at East and West Palo Alto. Yes, so for example, if you look at East and West Palo Alto and try to understand their insurance claims, yes? So clearly, the geographic proximity will be very, very bad metric to use, yes? Because although they're very close, you know, income levels desperately different. Yes, price of the houses is also, you know, desperately different, and so on. So everything is different, despite the fact that it's just like one stone throw away. Yes, so something else shall be done there. Okay, and so the idea is try to look at local neighborhoods of each node. In our case, this is the postal code, and group points, group nodes, based on how similar their shapes, local shapes. Okay. So, and here, of course, I bypassed, since we're in a TDA seminar, I bypass all the, you know, TDA concepts, because we're everybody's familiar with those. So essentially what we do, we create, we look at the neighborhood of each node. And after that, we look at all the neighbors within the neighborhood. And based on this neighborhood, we'll compute a Vittori strips complex, we'll run the filtration, and we'll compute persistent diagram. And there are many multiple ways, I mean, how you can do it. Okay. And so then you get a persistent diagram for each neighborhood, okay? And then the idea is that to group nodes with similar persistent diagrams, okay? So here we actually, despite the fact that usually persistent homology picks up properties that are global for, you know, for data cloud. Here, because we are doing it for each local neighborhood, you know, so we are, you know, kind of boiling it down just to local properties and then trying to match those. And so essentially, after you computed all these persistent diagrams for local shapes, for local neighborhoods, after that, you can apply any type of clustering. So we started from single linkage clustering, okay? And let me show. So this is roughly like visualization, a cartoon, how it works. You'll have all these points, and then some of the points obviously are much closer in terms of median distance, but we look at shapes of those points. And we cluster just, you know, hearts with hearts, moons with moons, clouds with clouds. Okay, and this is a you know, pipeline how we are doing it. So from multi-layer network to embedding, then to each local neighborhood, then PDs, and then we do single linkage clustering. This could be done anything else. It can be done hierarchical clustering, it can be done k-midoids and so on. And I'll talk about that in a second. Now, if we compare it with benchmarks, okay, so all the benchmark clustering usually is done, it's Euclidean, typically Euclidean clustering, k-means, k-means, hierarchical, and so on. Of course, you can do tomato and so on, but those tools are also in conjunction with some other, clustering algorithm. So here, right now, we're just comparing to this, classical Euclidean-based clustering. And as validation metrics, we can use within sum of squares and between sum of squares the ratio. So lower within sum of squares and high between sum of squares is telling you that actually you have a better type of clustering. And so this is the results for this climate insurance case. So we found that if you use this clustering with persistent diagrams, with local persistent diagrams, you tend to have better, much tighter clustering than based on Euclidean distances. So, and can you say hierarchical clustering or Euclidean k-mean-duets. We also compared that to local topological k-mean-duets. So where instead of single linkage clustering, we're trying to minimize the distance between local persistent diagrams from each point. And this version of topological clustering also works pretty well on par with single linkage topological clustering. So we have like roughly say 3 times higher DSS than our algorithms, and much better clustering ratio for both CPD and topological k-mean-duets compared to Euclidean-based clustering. And actually, this is a distribution, spatial distribution of these clusters. And here on the top panel, you see topological clustering, then topological k-mean-duets, and then two other hierarchical, C is hierarchical, and D k-mean-duets. So you see that, for example, for hierarchical and for usual k-mean-duets, it tends largely to put everything into one big cluster without really accounting for very complex socio-demographic patterns that you observe, especially in Southern Ontario and Greater Toronto area. And so essentially like a hierarchical clustering clearly is out of business here. K-mean-duets is better, but still you see it still largely tends to put everything into the clusters based on just the geographical proximity, okay, not distinguishing that much. While topological k-mean-duets and CPD, single linkage clustering, they account for like subtle patterns especially in Greater Toronto area, when some areas, for example, High Park, tend to be much more expensive than others. And then you start seeing them when you look at the plot, when you use topological clustering. And there is much more like a comparison in the paper, which it shall appear in PNAS soon this year. Now, so this is of course, it's a nice example how you can do topological clustering on multi-layer network. And obviously, of course, you can do it for point clouds, for functional data, and so on. Do it locally. Essentially, I don't care about it's not like I don't care. I mean, I care about the proximity, of course, but not only proximity. I care about the shapes. So if, for example, I'm trying to cluster something on the graph on Facebook, so I'm not simply looking at Henry's as a node, but I'm looking at, say, Henry and Sarah interaction and how their neighbors interact. Just think about if somebody is trying to do matchmaking agency. So it's not you're simply connecting male and the woman, yes, man and the woman, but you try to look at the shapes of everything via families, peers. It's a very complex interaction, yes? And then you try to match values. So that's roughly the idea. But now, what about stability? And stability in a statistical sense, not in terms of persistent homology, but in statistical sense. So what if I do multiple type of random sampling out of my data and I do clustering? Will I get the same stuff or not? Okay, I don't know. And actually, it's a very important thing. So clustering stability generally, so there are two main results in general clustering framework, not only topological one. It's asymptotic consistency. So if we assume that we have some clustering loss function and it's unique, it's a big assumption by itself, going back to Pollard paper 1981 and also statistics. So you need to have an assumption that you have unique minimizer of your clustering loss function. So if you do have it, okay, will my empirical minimizer converge to the population minimizer or not? That's consistency. And very related thing to this is stability, in the sense that if I do multiple independent samples from the same population, will I get the same stuff or not? On average, that is stability. So this is, again, this general things that we'd like to have and that we don't. So let's look what happens in terms of Euclidean clustering versus topological clustering. So obviously there are no results on clustering stability for single linkage clustering because we don't have even a loss function there. Yes, so, and that is both for Euclidean and topological case. So if you'd like to have some kind of asymptotic results there, you need to have a loss function. So it shall be either k-means or k-means or something around this. So Euclidean k-means is shown to be both stable and consistent. So those results are about 15 years old. And we go to Rachley and Component and Ben David had multiple papers on this. And there are different ways how to prove it. So some arguments are geometric and some are algebraic. But those results hold, okay, for k-means. So now if we look at topological clustering, there are no statistical stability. We don't know what happens really in terms of consistency, and we don't know in terms of clustering centers either there. Of course, there exist methods of k-means in the space of persistent diagrams. They are not local, but it doesn't matter for theoretical purposes. It doesn't really matter that much. And both, for example, fuzzy k-means and hard k-means, these results, those papers have convergence guarantees that k-means in the space of persistent diagrams will converge, but we don't have any stability results. So how we can address this problem? So actually this problem I was thinking about for a year, how to do it. Clearly, you cannot do it in the space of persistent diagrams because it's not a nice space, it's not a Hilbert space. You cannot use all the tools there. So how to do that? So I was thinking of using persistent landscapes. That's one way of doing it. And then we came up with the following idea. We actually will pass this k-means in the space of persistent diagrams to reproducible kernel Hilbert space. Okay, so, and then we'll have all these nice results about uniform Glivenka, uniform Donskiy. We'll have results on it's actually going to be VC type. And so what we are doing here is it's pretty intuitive idea. So we actually kernelize. I'm running out of time. So we are kernelizing the PD. Okay, so. The following way, okay, so essentially we're putting in correspondence, you know, function f, okay, in our Hilbert space for kernelizing each particular element within the PD, okay, and as a result, we are finding ourselves now in RKHS, okay. And then we have all the nice results that we need about uniform convergence there, okay? So we defined the distance between two local PDs through the corresponding inner product. in our HS, reproducible kernel Hilbert space. And instead of minimizing the distance with among PDs as before, for example, as midoids as we have done before, or through, for example, you can do it for free means, of course, as well. But again, for free means, if you're minimizing through those, you still don't have any results on statistical stability because you don't have any. You cannot get results on covariant number or uniform Glivenko-Cantelli or Donsker. So instead, I said, like, we are looking at the distance between PD through the distance between their kernelizations. And we minimize the distance to the center, and then we get the k-means in the Hilbert space. And after that, so essentially similar to Euclidean space, but we're bringing everything to Hilbert space. So we have a class of separability functions, okay, that distinguish our type of clusters. And we can show that this class, tau k, is over isotropic Gaussian kernels. It's important that we use Gaussian kernels because we have results on C universal kernel immediately. So it's P Donsker, and then it's also Wapner-Chernovensky step, okay? And as soon as you have this, you immediately can get result on consistency of topological k-means, local topological k-means. And also, if we assume that there exists a unique minimizer for a population, then we also get the stability. So our clustering centers from topological k-means from kernelization do converge to each other. Okay, so they cannot be too different from each other. And so the last example that I'd like to show has nothing to do with networks. Therefore, actually added this beyond networks because everything that I show here is not restricted to networks. It's just that we started from networks, from a very practical problem. So that is clustering of COVID-19 data states. Yes, so we looked at Johns Hopkins data, multiple number of people and some of the social demographic variables and observed number of COVID cases, suspect number of COVID cases, and so on each day. Okay, and we looked at multiple type of clustering. So k-means, the usual Euclidean k-means, hierarchical clustering. K-means PD. So here you simply vectorize each PD, similarly as persistent image, Henry, as in your paper, and you vectorize. You have you vectorize PD, and then you just apply the usual k-means to this Euclidean k-means to this vectorization. TOPO-CBN is our Yulia method where we looked at clustering, local clustering based on Bethe numbers instead of persistent diagrams, and this version where we use reproducible kernel Hilbert spaces. Okay, so this all based on silhouette index. It's internal measure for clustering validity with Euclidean distance. And here's a change where in silhouette we use topological distance instead of Euclidean distance. And you see that in many cases, I don't want to say that our topological k-means always outperform. It cannot. Nothing will be perfect. Nothing will be always great, but it certainly works pretty competitively. In many days, picking up, suggesting a better clustering in terms of silhouette. And it's interesting that if you plot this data, it turns out this is our case, and this is hierarchical clustering. And you see that hierarchical clustering, as before, tends to put way more states just in the one cluster, while topological clustering tends to differentiate between different states. And actually, remember, it's like early January, mid-January, and so there were more cases in Florida at that time because people traveled from New York to Florida for vacation and they didn't have any lockdowns and so on. That propagated into Georgia and so on. So it's actually very interesting that sometimes by using this topological distances, you can actually pick up some patterns that you are not able to pick up with like standard off-the-shelf Euclidean tools. Okay, and so to conclude, I think that there is still a huge gap between, say, statistics and tools of topological data analysis, even applied topological data analysis. And statistical topological clustering has many interesting perspectives on low-hanging fruits. So clearly, one application, one very interesting direction for TDA is dynamic space-time clustering. Okay, especially for very disparate data, including when you have something of very, very different nature. For example, you have something from cyber physical systems and something from social demographics. So data completely different, but nevertheless, you know, and so using Euclidean metrics won't be a good thing to do, but trying to understand shape patterns through TDA may be very helpful, especially when the type of clusters change over time or space. Okay, and particularly for and when density of clusters changes well over time. Then the next interesting thing that we try to look at is selection of a number of clusters, number of partitions in topological clustering. There's a huge work, I mean, many papers on doing that, on optimal number of cluster selection in Euclidean clustering. And people use clustering stability and consensus for addressing these problems. Can we do something like this for topological clustering, for topological k-means? Okay, either in reproducible kernel Hilbert space or in a persistent diagram space. I think that's obviously it's easier to do it in Hilbert space because of the stability properties, but nevertheless. Then the area which is completely untouched right now, to my knowledge, is topological methods for internal clustering validation. Okay, so can we use topology? I mean, not only topological methods for clustering, but topological methods for cluster validation. Maybe you can do clustering based on Euclidean metrics, but can you have a validation metric, internal validation metric, to understand how good is your cluster based on persistent homology? And then, of course, topological dimension reduction information loss, because when we do clustering, you obviously lose some of information. So how much of information you lose? Okay, and how you can quantify it. So, and this is the team. So some of Yuju Chen, my collaborator from SMU, my former postdoc Ocean Day, Matthew Dixon, former postdoc Slava Lubcic, collaborator from Vincent Poor, and my former student who is in Uber right now, Manish Viraj. Thank you.
Thank you very much, Yulia, for the fantastic talk. Before we get to questions, let's briefly unmute ourselves and applaud. Wonderful. What questions do we have?
I have a question. Here, let me turn on my camera so you can see me. Great talk. I really enjoyed it. I do have a question just regards to, you know, can you say something about the subpopulations with respect to their, you know, topological signature? Was there some meaningful correlation between the different topological signatures and those, you know, clusterings?
In which one? You mean in insurance, climate insurance?
Yeah, in the insurance.
Yes, of course. Yes, yes. It's actually the signatures based on. So you see, the goal is actually to make the parallel maps eventually. Although we have not came to the question of creating really risk maps because we are providing it to insurance company. But the resulting clustering results I would say correlated, because correlated is not really the proper word here from statistical perspective, but it actually mirrors the risk analysis for insurance losses.
Yeah, so I guess I'm wondering, like, what's driving cycles, right? Like, is there some clear, pointer or factor in the data that's driving those cycles?
Let me go from a slightly different state. So yeah, I cannot say what driving the cycles because there is a very complicated interaction between multiple variables here. Okay, so age of a house, yes, in the area, income level, data only 10 years old. Okay, so we we don't need to worry about trends and so on. But nevertheless, and so for example, urban infrastructure in the area, yes. And then precipitation, where it is. So latitude, longitude, and how that affected the precipitation. So imagine that you have a house that on a hill. Although everything is the same, but your house is on a hill. And the neighboring house is not on a hill. Okay, so you will be much less affected by flooding. So if you do the Euclidean ones, you will never pick it up. But if you look at the shapes of the neighborhood around you, okay, you may pick up those interactions better. So I won't go into cycles from a persistent homology perspective here, because I cannot, it's too abstract for this problem I mean, I cannot say what is the cycle here for this type of dependency. But you are, from a statistical perspective, say usually people in geostatistics, for example, or in standard statistics, they look at most moments, yes? So we look at the, the simple proximity, so simple type of dependence, like just pairwise. Here you are dependent and much more like a graphical model. You're dependent across many other things. And that's why we are doing multi-layer network, to try at least to approximate this complicated dependency. But then we are doing TDA to understand better so that we are looking at the not just pairwise proximity, but shapes, which may potentially pick up something like changes, for example, differences in latitude, differences in some areas because of a school discrete are more popular than others.
Yeah, so like, I guess
more people are moving there that have a high income level, and then they invest more into their houses, which we probably don't see, but that may be picked up by using topological distances, by shape similarity, let's put it like that.
I imagine that the insurance folks, they want something like to point to, right? To say that, oh, these data are the same because of blank, right? And so like, I've applied, persistent homology in psychology, and it's almost the same thing. They say, why are you getting clusters of these folks and not these folks? And so one idea, and it's just a really coarse idea, that, multi-dimensional scaling, what they'll do is they'll just correlations in the data, right, with each dimension. So they rotate the data and they say, does this factor correlate highly with direction? And I think you can do the same thing or something similar with each cycle, right? Which is rotate the cycle until you get something that kind of looks right.
Yeah, I agree. But it's actually working with insurance company was very interesting, because the team they all have PhD in insurance math, pretty much, or actuarial science. So they actually, their goal, they know the data very well. They are not looking at correlation, because correlation for them, we have premiums like a short-term planning, medium-term planning. So when we look at the cluster type, or how they cluster, we see that it makes sense to them by whatever reason. For example, oh yes, this is the area that lately we got so much, yes, comparing to to this area. Yeah, this is like something for our business purposes that we observed before, that this area by whatever reason is similar to that.
Awesome. Okay, great.
Okay,
Thank you.
so the idea is, yeah, so, but I completely agree that when you're trying to do this kind of analysis, for example, on say, something like a joint Facebook, Instagram, and so on, then what you are saying, doing the cycles obviously makes a lot of sense.
Thank you.
More questions? Yes, I see. Nahid, you have your hand raised. Please go ahead.
Hi, Julia. Thank you for the nice talk. So I'm still trying to understand the part about like the motivation behind using topological based clustering, because I think if I'm right, you are doing the clustering in the Euclidean space, right? You transform the multilayer network by embedding it into the Euclidean space. Am I correct?
Yes.
I see. So,
but when you embed it, it's no longer, you try to preserve certain proximity of nodes, so certain, dependency of nodes in the embedded space, but it's not the same as the original multi-layer. You don't have a graph structure. It's almost like you're moving from a graph to say Laplacian.
I see. So can I think about it like you are sort of, this embedding sort of eliminates the complexity of the multi-layer network in some sense?
That's the only reason. That's the only reason of doing it.
I see.
That's the only reason of doing it. The only one. But after we have done this one, we have looked at actually on an actual graph without doing any embedding. So we looked at the local neighborhoods. We picked up shapes so we looked at either power filtration, or we looked at persistent homology invoked by attributes of your neighbors. And so then we associate this persistent homology of your neighborhood with your node, with you, for example. Then when we did multiple things on this, for node classification, for link prediction as well. But say you can bypass, if you don't want to work with this like a huge thing as a multi-layer graph, you can do the embedding. Again, that was just applied motivation for us. But you, generally speaking, can bypass it. You don't need.
Okay, thank you.
More questions?
Actually, I want to say is that in infancy, when you look at the multi-layer graph, yes, especially multiplex graph in our case, because it's easier. So you can actually apply multi-persistence across different type of dependencies, yes. So that will be perfect way of applying multi-persistence, because you have dependency across one node of multiple types, and you can explore that and do it within locally, within each local neighborhood, and then get this topological feature associated with either as a persistent diagram or landscape, or using this kernelization.
Mm-hmm. I was wondering if you could explain. Oh, go ahead, Nahid. Sorry.
Sure. Yeah. So I was thinking, like, isn't to some extent the quality of the clustering is also dependent on the quality of the embedding?
Of course, but this is in any clustering. People in the standard graph clustering, they look at Laplacians, yes, and they have different results depending on what type of Laplacian you have in reality, yes, of course. What type of embedding you do will depend, yes, but we do say it's normal. It's not a problem of topological clustering. It's just a general. How good is your embedding? But it's different type of embeddings.
Right. Yeah. Thank you.
I wanted to ask about this map into the RKHS space again, this kernel. So you're doing this on the local persistence diagrams. Could you explain this map again briefly?
Essentially, yeah. So the idea is that we are looking at a kernel, you're kernelizing each feature in it. Okay, and then because we use a Gaussian kernel, so you have a universal kernel, and it's also associated with a Bochner integral, and so then you have all the results there. Of course, there are complexity issues, so there are some ways of doing it simpler way, but then if you aggregate, then you also lose information, so it's like a trade-off.
Thanks. More questions? Well, if not, thank you so much, Yulia, for a fantastic talk.
Thank you. Thanks for inviting. I enjoy the seminar series so much. I try to wake up by 10 and